Hello and welcome to this webinar brought to you by the IEA 4E Mapping and Benchmarking Initiative. This briefing describes an international comparison of the energy efficiency of distribution transformers and the associated policies, which was carried out by the IEA 4E Mapping and Benchmarking Initiative, working in close cooperation with the Transformers Working Group of the SEED Initiative, which is the Super Efficient Equipment and Appliance Deployment Initiative. My name is Jeremy Tate, and I am one of a small team who work on this collaborative international initiative, which is the Mapping and Benchmarking Initiative. And this is carried out for the benefit of policymakers who are responsible for developing the policies relevant to these products in the 12 participating countries. This particular study draws on data for over 14,000 transformer models, which were drawn from Australia, Canada, India, the Republic of Korea and the USA. And it looks at the policies that are in effect in those markets, as well as the policies that are currently in effect in Japan and the EU. The main report, which is the subject of the webinar, was published in April 2014 and is available free of charge at the Mapping and Benchmarking Annex website. The agenda for this webinar is shown here, and we'll start with some information about a study which was carried out during 2012 and 2013 by the SEED initiative and really formed the foundations on which the mapping and benchmarking study was based. This first study by SEED looked at comparing the policies and the thresholds in current policies and worked out the methodology to normalize these thresholds in order to make them comparable on a fair basis. It also developed a framework for comparing the performance of policies around the world, a set of tiers of performance that can be used by policymakers as a reference framework when developing their own local policies. In the mapping and benchmarking study, which built on that, we were able to take that methodology and the framework of tiers for performance and show how those compare with real product data drawn from the participating countries. And in order to explain this to you, we're going to be going through the sections you can see on this slide, starting with a description of exactly which products are included within the scope of the study. We'll talk about the data sets that were made available to the study from each country. We'll talk about how these different data sets can be made comparable through a process of normalization. And we'll talk about the metrics that were used as the basis for comparison and why we use those particular metrics. And then we'll look at the policies and the minimum performance standards that are in force in the participating countries. And we will then take a look at how the efficiency results from those countries compare with respect to the minimum performance requirements as well. Then we'll move on to compare how this performance data from real products fits and compares with the efficiency tiers that were proposed under the SEED initiative. And we'll finish with some observations drawn from the work which policymakers may find of interest, and finally a few opportunities for policy development that were identified through the work. So firstly, looking at the SEED work which was carried out during 2013. For those of you who are not familiar with SEED, it is a 5-year $20 million initiative which is funded under the Clean Energy Ministerial and the International Partnership for Energy Efficiency Cooperation. SEED works to turn knowledge into action to accelerate market transformation through effective appliance and equipment efficiency programs. It is a multilateral voluntary effort which has input from Australia, Brazil, Canada, the European Commission, France, Germany, India, Japan, South Korea, Sweden, the United Arab Emirates, and the United Kingdom and the United States. Now, the purpose of this particular initiative under SEED, this Transformer project, was to develop technical resources for policymakers, those who are responsible for establishing energy-efficient transformer policies and programs. It was a 12-month study and was published in December 2013. And basically it compared the efficiency programs and policies all over the world by normalizing the requirements to a common comparable metric. The final report for this study is in 4 parts. Part 1 is an efficiency comparison, comparing the similarities and differences between the test methods and the efficiency levels that were found. Part 2 goes into more detail about the test methods themselves and discusses the key parts of those and how they are used for measuring efficiency. Part 3 is where the international framework tiers were developed. This is a means to compare the markets around the world, giving policymakers a framework, a reference framework for efficiency, which they can use in developing their own policies. And finally, Part 4 provides profiles of the participating countries, summarizing the programs that are reviewed as part of the study. So the SEED initiative provided an excellent technical foundation on which the mapping and benchmarking initiative could build. And so now we'll look at how that was applied in the mapping and benchmarking initiative. So first of all, the scope of products that are included within the study basically met this definition. And the scope was focused primarily on medium voltage transformers between 1.1 kilovolts and 36 kilovolts of voltage, and in terms of capacity it was generally focusing on those between 10 kVA up to 2.5 MVA. Now this the study covers both liquid-filled and dry-type transformers. It covers single-phase and three-phase, and data was certainly invited on both pad-mounted and pole-mounted transformers, although in fact no data specifically relating to pole-mounted was submitted. The study specifically excluded any specialist transformer types, including the Scott T transformers, auto transformers, welding transformers, etc. They were excluded. And we did get some data on low voltage dry type transformers, but these were not included in the study as they were only relevant to 1 or 2 of the markets included. Now, the datasets that were received were from 5 different countries, shown in this bar chart here, and the height of these bars shows the count of models that were included in each dataset. You can see that the USA provided a dataset which had over 8,000 models in it, but the majority of those were actually liquid filled, which are shown by the semi-transparent coloured bars, and the dry type count is shown by the height of the solid colour bar. So USA had the largest quantity of products. The Australian dataset had not so many products, with only 340, but as you can see from the relative sizes of the transparent and solid colour bars here, around 85% of the models in the whole dataset were liquid filled, with only 15% of dry type. And indeed the USA dataset accounts for nearly 70% of all of the liquid type models that were analysed. And in fact it was Korea that accounted for nearly 3/4 of the dry type models that were analysed. And in terms of the number of phases for which the products analysed were designed, the majority of the products that were analysed were of the three-phase type, with only 30% of the liquid-filled and 3% of the dry type being single-phase type products. So now we're looking a bit more detail at the data sets that, and you can see from this table that all of the data sets actually came from governments or from government managed certification databases. The data was invited in July 2013, with some additional data provided up to January 2014. We are pleased to have included some data from India in this study. India is not a country that participates in the Mapping and Benchmarking Initiative generally, but we were pleased to be able to include some Indian data here. You can see by this summary table so a little more detail on how the coverage by each country varies. For example, in the Indian data set, it covers only liquid-filled products and also only up to 200 kVA in capacity, whereas the Australian data set, for example, covers liquid-filled and dry and covers up to 2,500 kVA. Similarly, the Canadian data set only covers dry type, although it does include a lot of larger capacity products. And in fact, if you look at the right-hand column of this table, the average capacity of the whole data set for each country, then you can see that there was a significant variation between the data sets in terms of the average capacity. The Canadian products are clearly generally of a higher capacity than the Indian products, for example. And this gives particular challenges in terms of comparing the data sets on a fair basis. I mean, one of the main objectives of the mapping and benchmarking activity is to enable a fair comparison between countries of performance of markets, and clearly we cannot attempt to compare these whole data sets between these different countries because they are very different in their makeup. So for all of the analyses that you will see during this webinar, each graph is focused on a very specific subtype of product, and those plotted on the graph are generally comparable on a reasonably fair basis. So if we want to include India in a comparison, we have to limit all of the data sets that are shown in that graph to be only of the smaller capacity range, and you'll see that as we go through. Now, there was no year associated with any of the data sets in particular. The data represents a snapshot of the products available in the data sets of these countries at the end of 2013 or beginning of 2014. And so this is different to the analyses you may be familiar with under other mapping and benchmarking activities, which tend to look at longer term trends in performance, whereas this is a snapshot at a particular moment in time, and I think fairly reflects the relatively slow pace of development of transformers and transformer technology, other than associated with particular policies coming into force. Now, as with all of the product studies that are done under the Mapping and Benchmarking Initiative, we do aim to provide guidance for readers in terms of how robust they should treat the data that is given for each country. So this is a representation or a qualitative assessment of how representative the data sets are of their local market. And we use three sort of quality classes, if you like: the robust, indicative and illustrative. And this table shows how the different datasets were assessed under that grading system. You'll find a lot more detail about the definitions of the gradings in the main study. You can see that for the liquid-filled products, we have 3 datasets that were considered indicative. Incidentally, none of the datasets were considered robust, because a key part of our definition of robust is that the datasets are sales weighted, but we had no sales data on these products for any of the datasets. It was only a list of the models available in that dataset. So none are robust, but we do have 3 indicative datasets for liquid filled for Australia, Republic of Korea and USA. So that means that they're pretty well representative of those markets, with certain caveats that are evident from the previous table that you've seen. The Indian dataset gets an illustrative rating because it's only a partial market for liquid filled. And of the dry type, we only have 2 datasets that were considered indicative. That's Republic of Korea and USA. The Australian dataset for dry type consisted of very few products indeed, so was ungraded. So because of this lack of comparability, we certainly show graphs that are coming up shortly, split down into only liquid or dry type and only 3-phase or single-phase type. And we also split the data by for dry type by basic impulse insulation level, the BIL category, in order to further ensure that the data being presented in any particular graph was comparable on a fair basis. Now, in terms of rendering the data comparable, it wasn't simply a matter of sort of splitting down by categories. We did also have to make some adjustments to compensate for difference in the test methods. Now, the test standards, the test methods used in Australia, EU, India, Japan and the Republic of Korea are based on the IEC family of test methods for transformers, whereas those for Canada and the USA are based on the IEEE test methodologies. And similarly, we did have some difference in the metrics used. Those for Australia, Canada, Korea and the USA do use a percentage efficiency, whereas for India and Japan the performance of the transformers is expressed as a maximum total core losses and coil losses, and indeed for Europe there are separate maximum core and coil losses used as the metric there. So in order to make these comparable, some adjustment was needed, and the details of this are explained properly and fully in the both in the seed transformer study, which was used as the source of the analysis method, but also explained in the mapping and benchmarking report. But in very brief summary, we adopted the IEC definition of kVA for capacity, which is based on the power input to the coil. So those based on power output were adjusted as required to make them comparable. And the metric that was adopted was the percentage efficiency at 50% load. And it's a relatively straightforward calculation to generate a percentage efficiency at 50% load from the core and coil losses which were available in some of the data sets that were used. In addition, for the IEEE based results, there was a temperature correction applied for the winding reference temperature used during test. Once again, this was a fairly straightforward adjustment made only to the data from Canada and the USA. We made no adjustment for the supply frequency, 50 Hz or 60 Hz, for the products that we analysed, because this is inherent in the systems in the country, and so it's not something that we would normalize for in any of the studies that we do under mapping and benchmarking. So the conversion calculations for this were fairly straightforward and resulted in no loss of robustness of the input data. They were all based on firm physics, and so did not involve any assumptions or approximations. So the main metric that was used, as I've said, was the percentage efficiency at 50% load. But we also developed an extra metric which was used to compare the average efficiency between the different data sets, between the categories of products within the different data sets. And for this, we generated an energy efficiency index. So this is a new index which was developed under this work collaboratively between the SEED team and the mapping and benchmarking team. And this basically uses a reference efficiency level from the SEED tiers of efficiency. So we used SEED tier 1, which is basically the level of performance which corresponds with the lowest OECD performance level that's seen in policies around the world. So we took the efficiency at 50% loading of every particular model, and we divided that by the efficiency that would be achieved by a transformer of the same capacity if it complied exactly with the SEED tier 1 efficiency level. So that created an efficiency index, and then we weighted those efficiency indexes by the capacity of that particular unit. This is because the performance of a very high capacity unit will make a bigger difference to the performance of the national portfolio of products than will a very small capacity product. So we took the kVA rating of that particular model, multiplied it by the energy efficiency index. We took the sum of all of those weighted indices from the whole data set and divided it by the total sum of kVAs for that whole data set. This provided a capacity weighted energy efficiency index and was used to compare markets. Now, the policies in effect in the countries that participated, plus the EU and Japan, are summarised very briefly in this table. We do give much more detail in the mapping and benchmarking study reports. Basically, there are minimum requirements in force in Australia, Canada, the Republic of Korea, USA, and we have the top runner scheme for requirements in Japan. We will have minimum requirements in the EU coming into effect in 2015, and there are no mandatory requirements as yet in India, but India does have an energy labelling scheme, as does the Republic of Korea, and the scheme in Japan is a voluntary scheme and has been in operation since the year 2000. So we now have a series of 3 slides which compare the thresholds of various policies that are in force around the world to see how they compare. And the thresholds as published in the policies have been adjusted as necessary according to the normalization process that we described earlier to make them comparable on a fair basis. And what you're seeing in this graph is on the vertical axis you're seeing the percentage efficiency at 50% loading. And as you can see, the efficiency levels range from sort of 98% up to 99.5% for this particular type of product. And on the horizontal axis, you see the capacity rating in terms of kVA, and this is plotted as a logarithmic scale, which just gives a more easily understandable and clearer set of lines to compare. So on this particular graph you are seeing three-phase products of the liquid-filled type only. Now we're seeing lines for Australia, for the EU, for India, Japan, Korea and the USA, and it includes some standards that are in force now or that came into force in previous years, but also, particularly like for the example of the EU, these are regulations that are not yet in force. So looking at in particular types of study of performance requirement, if we look at the green line, which is that for the Republic of Korea, the requirements are set at a much lower efficiency level than all of the other participating countries that you can see on this graph. And also the requirements for the EU, which is shown in this in the brown dashed line for 2015, you can see that for most of the capacity range these are reasonably comparable with other existing standards, but below around 50 kVA the European requirements do dive quite a bit less stringent than those of other nations. If we now look at the requirements for single-phase liquid-filled transformers, you can see once again that the Korean requirements are substantially lower than the requirements in the other participating countries. And well, there are some interesting observations to draw when you start comparing the performance of the whole market, and we'll come to that in a moment. But also you can see that the pink dashed line that you can see there, which is the USA requirements for 2016, these are the most stringent amongst those analysed in this data set. Now looking at the requirements for three-phase transformers of the dry type, this particular graph involves consideration of the BIL rating, the BIL rating, because efficiency varies with BIL rating, and so strictly speaking only comparable BIL ratings should be compared. But unfortunately the policies don't subdivide into sort of simply comparable sets of BIL ratings, and so these are shown as different line types in this graph. Overall, the requirements for dry type transformers are more consistent between countries, and they are closer together, including those for the Republic of Korea. But once again, you can see how the requirements for the EU are or become significantly less stringent below the 100 kVA capacity rating. If we look at the top runner requirements for three-phase dry type, you can see that these are the most demanding, the most stringent requirements amongst the countries that are shown in this graph. So now we are starting to look at the product performance data from the models provided in the national data sets. In this graph, we are looking at the performance of 8,400 different models from the datasets submitted. We're only looking at liquid-filled and three-phase transformers, and this was the dominant type included in the across all the datasets. The MEPs shown in the in this graph are only those relevant or applicable at February 2014. Now, as you can see, the Korean models span a very wide range of efficiency across all of the capacity range that's shown above 100 kVA. And it's interesting to note that the vast majority perform significantly better than the local MEPS level, which is the green line at the bottom of the set of data here. But the majority of these models registered do perform at levels lower than the requirements of Australia and the USA, which is shown in the red line and the purple lines. But if we look, if we zoom in more closely at the higher efficiency region of this graph, so this is the same data, just zooming in to the higher efficiency levels, you can in fact see how the Korean models, which are the green diamonds, are actually jostling amongst the very best of the USA and Australian models. So despite significantly lower minimum requirements, it's quite clear that the Korean market has products that are just as good as the best in Australia and the US. So this was looking at the sort of scatter plot of all the models included in the data sets. The next graph is our use of the energy efficiency index to look at the average for each country's. So this is the energy efficiency index, and this is looking at liquid-filled three-phase models, and only those below 250 kVA capacity. And this is because we are including the products for India, which, if you remember, only includes the smaller capacity units. And so in order to be fairly compared, the datasets averages have to be filtered to contain only products of that range. And you can see how the results for the capacity weighted energy efficiency index for Korea reflect what you'd expect based on the graph you've just seen, in that their overall average is lower than that for Australia, India and the USA. And in fact it's lower than an index of 1, which would be equivalent to the seed tier 1 requirement, which, if you remember, was the level which corresponds generally with the lowest level of minimum requirements for the OECD countries around the world. So bear in mind when you're looking at these averages that the Republic of Korea dataset includes products that match the very best of the Australian and USA markets, but nevertheless that overall average is significantly lower. Now this slide is looking at the efficiency of liquid-filled single-phase transformers, And this graph shows the performance of 3,500 models, and 90% of the models shown on this scatter plot are from the USA. As you can see from the groupings there, the Australian products are only in the much lower capacity range, and cover a narrow range of capacities. The Korean data once again is shown above the Korean minimum standards, which are significantly lower than those of the other countries. But once again, the Korean data has products that are certainly very high in the efficiency ranges, even if not completely matching or beating the efficiency of the USA models. If we now look at dry type three-phase transformers, for this particular graph we have filtered to include only those with a BIL rating of 20 to 45 kilovolts in order to ensure reasonable comparability. This particular chart shows maps, both mandatory minimum for the green line for the Republic of Korea, but we also show a pink coloured line, which is the target energy performance standard, which is this higher level of performance for the Korean market. Now, in this graph you can see that the USA and Canadian models have a very similar range of efficiencies to each other, but in particular, if you focus in on the higher efficiency areas, you can see how much better the Korean models are in general than those of the USA, the Korean models in green, the green diamonds. These extend to a far higher level of efficiency than the Canadian and USA data. So then if we look at the average efficiency shown by that same set of data, you can clearly see how the Korean average is indeed well above those of the Canadian and USA data sets. All three of them being well above the EEI, the Energy Efficiency Index of 1, which is equivalent to the SEED Tier 1 requirement. So whilst the Korean dataset has products much more efficient than the Canadian and US models, its minimum requirements are by far the lowest of the three markets, but it does still achieve that overall average much higher. So clearly the Korean market must have other factors driving better efficiency than simply those minimum requirements. This chart is now comparing the SEED international efficiency tiers for liquid-filled three-phase products with the data that we have from the datasets for those same type of liquid-filled three-phase products. Now, these tiers were developed under the SEED initiative in their report, which was published in 2013. And these tiers are proposed for use by policymakers in setting globally comparable transformer standards. They are designed to help understand the range of product performance on the global market and how that compares with the minimum standards that are in place in many parts of the world. So the thresholds for these tiers are defined by a set of equations that were developed under the SEED initiative, and there are separate equations for single phase, for three phase, and for liquid filled and dry type, and also separate tiers for 50 Hz and for 60 Hz products. Now, this particular chart shows only the liquid filled three-phase curves, and you can see how the curves align fairly well with the available data. So if you just look at each of the tiers in turn, basically the tier 1 level aligns with the lower, not necessarily the lowest, because that was the Korean minimum standards, but with the lower minimum requirements in force in many countries in 2013. So it's basically presents a sort of entry-level minimum requirement for countries planning to set up new standards. Tiers 2 and 3 align indicatively with the minimum standards present in most OECD countries. Particular close examples in this case are those for Australia and for the USA. And up at tier 5, this basically aligns with the global best available technologies that are on the market as at 2013. So you can see that these tiers show the spread of performance on the market as at 2013, and show also where the minimum requirements are for most countries. As you can see in this graph, there are a substantial number of models from Korea that are actually pitched below tier 1. This graph now looks at dry type 3-phase products and shows the seed tiers that are proposed for those. And here you do see a significant contrast in the positioning of the Korean models compared to the others, as we saw in the previous example. Because in this particular case, you can see that the Korean data is actually bunched between tier 3 and tier 5, whereas the Canadian and US data is actually between tier 1 and tier 2 to 3, and shows the very different positioning of the Korean market compared to the others. This graph is looking at the seed efficiency tiers for liquid-filled 3-phase. Some policy lines have actually been removed from the figure in order to reduce the clutter and allow the remaining lines to be seen. Here you can see both minimum requirements and also some voluntary or aspirational standards shown on the same graph, and indeed this includes current and future minimum requirements, for example the EU standards not yet in place, and it shows the US figures for 2016. And similarly, once again, we see the dry type requirements for 3-phase products, once again showing the different BIL ratings used in many of these different policies. It's difficult to show comparable minimum requirements because of the fact that different countries use different categories of BIL rating, and so it's very hard to show directly equivalent policies on this sort of chart. Now moving on to a set of observations that were drawn from the analysis that was done under this mapping and benchmarking study. This is picking out the main observations. Many more are described in the benchmarking report itself. Now, having compared the available product data to the seed tiers as they were proposed, it is fairly clear that those do indeed provide a pretty robust indication of the spread of the market as it stands at 2013, and therefore provide a useful reference framework for the policymakers to refer to when they're designing the ambition levels for policies in any country that's considering it. It's also apparent from the charts that you've been looking at that the MEPs have eliminated poor products locally, but it's also very clear that all of the markets we looked at have access to highly efficient models that are significantly more efficient than the minimum requirements for that country. And this certainly isn't typical of all of the product groups that have been studied under this annex. In many cases, we do tend to see bunching of products just above the minimum requirements. Clearly, there are policies or market forces at work for transformers pushing performance significantly above the minimum requirements. And that's particularly true of the Republic of Korean market. The analysis has also shown that the methodology developed enables a fair comparison of models, and indeed that the normalization process is relatively straightforward for these products. And we certainly hope that the collaboration between SEED and IEA 4E has reinforced each other's areas of work and has been able to develop a useful policy information platform which policymakers around the world can then use as they develop their policies. And finally, moving on to identify some of the policy opportunities that were raised by the work. And firstly, yes, very much the seed tiers present an opportunity for policymakers to use as a reference framework. And looking at some specific country observations and opportunities, the Korean models that we have in that database, certainly some of them match the best in the other countries, but it's quite clear that the minimum requirements as set at 2012 are certainly relatively weak for the liquid-filled, and we do know that those standards are already under review in Korea. It's also fairly clear when you see the standards plotted together on the same graph in a comparable basis that those requirements due to come in force in the EU in 2015 are pretty weak for transformers at the smaller end of the capacity range. So there's scope there for making those more robust. And at the opposite end of the scale, the USA minimum requirements certainly appear to be ensuring very high efficiency for liquid-filled three-phase products over there. And whilst Canada has no regulatory minimum requirements for its liquid-filled market, it is worth pointing out that it does have a voluntary code that addresses those products, but nevertheless most other economies are certainly setting standards for their liquid-filled transformers, and Canada could well consider that for the future. And another country with its regulations under review is India. They currently have no cover for dry type, nor indeed for the larger liquid-filled transformers, but both of those aspects are under review, and it seems possible that India will choose to develop standards that match more closely the range used in other economies around the world. All of the information that you've heard about in this webinar is available in the benchmarking report for transformers, which is available at this website that you see on this slide. It's free of charge, and it's available alongside benchmarking reports on a wide range of other domestic and commercial equipment. And in addition to the benchmarking report, you can also find reports on the individual economies, the policies and the data for those economies. There is no separate report on the data for India because India is not a participating country, but the data from India is certainly represented in the benchmarking report for transformers. So finally, I would like to thank the Seed Transformers Initiative team for their invaluable support and cooperation in the work carried out for the mapping and benchmarking activities. We're very grateful to work with them. And if you have any queries or questions, then please do get in touch with us at the email addresses you see on this slide. Thank you very much for your interest in the reports. We hope you find them useful. Thank you.